In this video, I'd like to kind of get you jump-started on doing some of the problems that are at the very beginning of the book, the very first section of the book, section 1.1. So I'd like to essentially work on some problems from that section. Before this point, you should have really watched 3 videos. You should have watched my introduction to the entire course. The second video was an introduction to chapter 1. And the third video was an introduction to the kinds of things you're going to be doing on Mathematica. Actually, that second video, that was my introduction to chapter 1, has a lot of material in it related to the very first section of the book, section 1.1. So you definitely want to make sure you watch that second video, the introduction to chapter 1, if nothing else. You should have read section 1.1 before this point. Read through it carefully, worked on the Mathematica file. You'll get a lot more out of this video if you have done that already. So like I said, I want to work on some problems now to get you started. Sometimes the hardest thing in math is just getting started on something, just getting going. And the first kind of problem that I'd like to work on is essentially, well, it's essentially number 1 in the very first section of the book. I'll go ahead and label it with a 1. You might want to have your book out, and if you don't, you could pause the video and go get it. And open it up to the beginning of the exercises for section 1.1 and take a look at number 1. That problem is about population growth, the US population growth. We're assuming an exponential model for population growth. All right? If you've done your reading, if you watched that second video, the introduction to chapter 1, you know that the exponential model, and you can see this in problem 1 also, for population growth looks like that. Showing up big enough? Maybe zoom in once in a while to see that. It's a differential equation. dp dt equals k times p. You should identify your variables. T is the independent variable, that's time. P is the dependent variable, that's the population, in this case of the United States. You should identify units. In this case, it would be in millions, if you look at the data that the problem refers to. And K is a constant. It's a constant of proportionality between the rate of change of population and the population itself. You're saying the more people there are, the faster the population is going to grow. That should make some intuitive sense. The more people there are, the more babies will be born. So this seems at first glance like a reasonable model, but as with all models, you need to do some testing. You need to think about it, work it through, and test and see how it does. It's not going to be perfect. It's overly simplistic, but that's kind of the art of working with models, is trying to just see how things go and trying to tweak it if you need to. It's certainly simple. If you think about this equation a little bit, what you're saying is you're looking for a function whose derivative is k times itself. You're looking for a function, and I will abuse notation like I did before. P equals p of t, so I'm treating the p both as a dependent variable and as a function name. Just emphasizing that p is a function of time. You're looking for that kind of function that satisfies this differential equation, whose derivative is a constant times itself, for this particular constant that I'm calling k. This kind of problem can be easily solved just by guessing. We certainly know that e to the x is a function whose derivative is exactly equal to itself. E to a constant times x, or in this case t, is a solution. That's going to be a function whose derivative is k times the original function. The chain rule is what causes that to work. And the fact that the derivative of e to the t with respect to t is just e to the t itself. You differentiate that, you're going to get e to the kt. times an extra factor of k from the chain rule. That's the same as p times k, the same as the right-hand side of the differential equations. That one function is a solution to this. But it's not the only solution. A little bit of thought will reveal that I can multiply that function by any constant c in front and get another solution, because that constant gets carried along for the ride when you differentiate. If I also know my initial population, that's called an initial condition, I can find the value of that constant. I'm thinking of the p0 as being some fixed and known constant, and I'm thinking of the c as being an arbitrary and unknown constant. But once I know this fact that at time 0 the population is p0, I can substitute to figure out what c is. Substitute p0 in for p, and substitute 0 in for t. E to the 0 is 1. So c in this case is the same as p0. That doesn't always happen. The constant that you get, the arbitrary constant in your general solution, is not necessarily always equal to the initial value, but in this case it is. So my solution is p equals p0 e to the kt. If I think of p0 as fixed, then that's one function that solves both the differential equation and satisfies this initial value. It's the one function that satisfies that initial value problem. And now it can be used. In number 1, if you look at the details, it says use the information, the data about the US population in 1800 and 1900 to try to predict, model what will happen in the future, for example, in the year 2000. Well, if you look in the chart, in the book it says that the population in 1800 was 5.3 million. And in 1900, the population of the United States was 75 million. Now, we also, it is past the year 2000, we also know the population in the year 2000, that's in the table too, is 281 million, but that's not relevant to the point of this problem as far as actually coming up with a model. At the end, we will compare the results of the model with the actual population, but as far as coming up with the model the way they describe, we're just using these two populations. It's convenient to pick t equals 0 to correspond to the first year you have data, 1800. So I'm going to label that as time equals 0. And it's certainly convenient to use years, so 1900 is going to be 100. And then we'll want to figure out, once we've got the model, what our prediction is when t is 200. That will correspond to the year 2000. We'll just put a question mark for the population in 2000, even though we really do know it. All right, well, if you use 1800 and 5.3 million as your initial condition, that's your value of p0. If I had used some other time, like 1700 as t equals 0, but still use these data, it could be done, but 5.3 would not be p0 in that case. So it's going to be most convenient to use t equals 0 to correspond to the first year. Go ahead and substitute in 5.3 in place of p0, meaning you can write your model like that initially. But in order to use this model, we still need to know what k is. Well, that's where the other piece of information comes in. The fact that the population is 75 million in 1900 allows us to solve for k. Just set p equal to 75, plug in t equals 100, and we get this equation. Hopefully this is feeling familiar to you. This is the kind of thing you should have done perhaps a pre-calculus or calculus course before. The only thing that's really new is the thinking of it as a differential equation, and maybe you've even done that before. But if you haven't, now is your first time. We need to solve this equation for k, And I should have brought my calculator. Oh no, I forgot to bring it. Okay, well, we'll have to leave it in exact form. If you've got e to an unknown power equaling something else on the other side, you want to use the natural logarithm function. Take the natural log of both sides of the equation. Natural log of x and e to the x are inverse functions, so if I take the natural log of the right side, the inverse functions in a sense kind of cancel, leaving me with just 100k. So k is going to be 1 over 100 times the natural log of 75 over 5.3. Now you can substitute that in, and because I forgot my calculator, replace k with 1 over 100 times the natural log of 75 over 5.3 times t. That's going to be my model. In practice, you would estimate natural log of 75 over 5.3 divided by 100. I'm going to zoom in on that if you can't quite see it real well. You want to estimate that. You should stop the video right now and estimate it on your own. And well, once you've done that, then use it, plug in t equals 200 to see how it compares with the true population in the year 2000. I'm almost positive it's not going to be the exact same thing. It's going to be off. There's going to be an error. The issue is, how far off is it? Could be off quite a ways, actually. That's possible because this is such a simplistic model. Another kind of population model is called the logistic model. I talked about that also in the second video. That's a bit more complicated, but you would also hope, at least in certain circumstances, that it's a bit more accurate. Here was the way I wrote it in that second video. Essentially, it's going to be like an exponential model when p is close to 0, because this one will be close to 1, and it will act like an exponential model. But then when p gets close to n, this thing gets close to 0, and so the derivative gets close to 0. In fact, when p equals n, this thing is exactly 0, and dp dt is 0, and in fact it starts at 0 and stays at 0 for the slope forever. That kind of function, that constant function, is called an equilibrium solution. There are a couple of equilibrium solutions here. The constant function p is always 0, and the constant function p is always n. When you look at those equations there, when I write those, I'm not thinking of p equals 0 and p equals n as being specific numbers, even though 0 and n themselves are specific numbers. I'm thinking of those two equations defining specific functions, constant functions whose graphs are horizontal. Those are called equilibrium solutions. They make the right-hand side equal to 0. I did have in the second video the solution to this equation when you've got an initial value problem, p of 0 equals p sub 0, and it was kind of a complicated equation. You don't have to deal with that equation in this very first section of the book. Instead, you want to think about this qualitatively. I did some of that in the second video also. You want to think about what values of p will lead to a positive derivative, because they make the right-hand side positive, therefore making solutions be increasing functions, and what kinds of values of p make the right-hand side negative, therefore making the left-hand side negative, the derivative, leading to decreasing solutions. Graphing the right-hand side as a function of p, we saw as a useful thing to do. In this case, unlike the second video, I don't have a minus c there. I've got just kp times 1 minus p over n. There are exactly two roots at 0 and n. We see that the function on the right-hand side is positive when p is between 0 and n. So therefore, solutions are increasing in this plane. When p is between 0 and n, you're going to get solutions like this. Why they curve in the ways they do, I'll leave for you to think about from your reading for the moment. So when p is bigger than n, solutions are decreasing. When p is less than 0, they're also decreasing, though that's not relevant as far as a population model goes. So that's how the picture looks. Again, to figure out where solutions are increasing and decreasing, you think about where is the right-hand side positive, negative. And you're going to be able to figure that out in general when you've got the zeros determined. In this case, p equals 0 and p equals n. So a number of your very first written homework problems are going to be like this kind. You're going to have to figure out what does the graph of the right side look like as a function of p, or whatever the dependent variable of the original differential equation is. Oftentimes it will be y. Okay? And you'll think about what that graph looks like. This is not a graph of a solution curve. Instead, it's a graph of the right-hand side as a function of the dependent variable of the differential equation. T is the independent variable of the differential equation. P is the dependent one. But in this graph, we make p on the horizontal axis. And you can label the vertical axis with the derivative, dp dt. We see it's positive between 0 and n, and negative when you're greater than n or less than 0. And that's going to help you figure out, for example, I believe number 5 is one of the homework problems. And also later on, numbers 15 and 16, I believe, just double check that quick, are going to be a couple problems that you look at related to population models. You're not going to be able to find, you don't have to use the formula from that second video to solve those problems. You just think qualitatively. Think about what the right-hand side is doing. Okay, positive, negative, or 0. That allows you to solve those problems. You will also want to think about the kind of thing that I mentioned in the second video where I subtracted a c from this model to account for harvesting. Those come up in problems 15 and 16. What I'd like to do right now, though, is show you another kind of problem. And you don't have homework problems directly related to this, but it is an important kind of problem. And I do want you to study what I do here on this video. It's possible I might put something like this on an exam, because it is an important kind of problem. Radioactive decay. All right? Sometimes I'll assign problems related to important things. Sometimes I won't. If I don't, I'll probably try to get them in the video and remind you that you need to be responsible for them. This comes up in problems, it looks like 10 through 14 in the very first section. I didn't assign any of those, at least for this first time I'm teaching the class. In the future, maybe you're watching this again, and maybe I have assigned it for you. So it will be helpful, doubly helpful there. So you imagine a substance. Okay, I'm not going to specify what it is initially. Some isotope of some substance. I'm not going to say what it is here initially. It's decaying. Okay? The amount that's there is getting smaller over time. How does it decay? Well, I'm not a physicist. I think sometimes it decays like because certain elementary particles just start flying off, whether they be electrons or protons or neutrons. And I think maybe sometimes it might decay for other reasons, but I'm not going to get into that. The amount that's there is getting smaller. That's the point. If Q is the amount that's there, and T is time, then dq dt, the rate of change of the amount that's there over time, can be shown to be a pretty accurate model if you assume that this is proportional to the amount that's there. In other words, the more that's there, the faster it decays. There's some constant of proportionality that I multiply Q by to make this an equation. What kind of constant do I need there? Well, dq dt should be negative because the amount that's there is decreasing. The actual amount itself is positive. So I need to have a negative constant of proportionality. Now I could just write a letter and say it's a negative quantity, But it's maybe more suggestive if I actually put a negative sign there in front of another constant, like that, negative lambda, where lambda itself is a positive constant, but lambda itself is not the constant of proportionality. That's negative lambda. But to emphasize that I have a negative constant of proportionality, usually people write it like that. This equation, if you think about it for a minute, looks very similar to the population growth equation, the exponential growth equation. I've got a derivative of some unknown function equaling a constant times the function. In fact, the solution of this is really basically the same kind of function. I'll call it q this time instead of p. Q equals a constant c times e raised to a power. The power is the constant times t. The constant here is negative lambda, so I get a negative lambda times t. The c ends up equaling the initial amount. If q of 0 is q sub 0, then the constant c will be q sub 0. Because lambda is positive, however, by the way, k was positive in that last equation, because lambda is positive, therefore negative lambda is negative, this is not an exponential growth, but instead an exponential decay. Its graph will be an exponential decay curve rather than an exponential growth. Q sub 0 is the vertical intercept. And because lambda is positive, so that therefore negative lambda is negative, this is going to be a decreasing function, as you would expect, as time increases. Now, quite often, radioactive decay problems are stated in the following way. You've got a certain substance, like, now I'm going to get specific, like carbon-14, and you know, or scientists tell you, that carbon-14 has a certain half-life. And assuming I copied this down correctly, let me just glance in the book here real quick again. The half-life of carbon-14, which is an isotope of carbon, half-life is 5,230 years. Some of you probably know what this means. Maybe most of you. But some might not. I'll remind you or tell you right now if you don't. Half-life is a measure of how long it takes for half the substance to decay. So you've got, say, 10 grams at first. If it's carbon-14, after 5,230 years, there would be 5 grams, half of what you began with. Of course, that also means for those 5 grams, it would take another 5,230 years for that to decay to 2.5 grams, half of 5. So this is a basic empirical law. It's basically true. I'm not positive how close to true it is, but it basically seems to be true. It seems to be the case that half-life doesn't depend on how much you start with. I think in extreme cases, like if you only had a few atoms or something, it's not necessarily the case. But when you've got, you know, many, many atoms, it's going to be pretty accurate. How do we use this here? Well, if we've got carbon-14 like this, and we've got the model set up in the way we do, we can use this half-life information to figure out what lambda is, the decay rate constant. How so? Well, here's your model that comes from that differential equation. Again, you may have talked about models like this in a pre-calc or even a calculus course without a differential equation, but we can certainly relate it to differential equations as we're doing here. We want to use that formula. I don't care what Q0 is. All I care about it is that after 5,230 years, q is 1/2 q0. So I replace the q on the left-hand side of the equation with 1/2 q0 and replace t with 5,230. Lambda still needs to be there though. Lambda now is really what we want to find. And notice the q0 is irrelevant. It divides out. Assuming it's not 0. So I get 1/2 is e to the negative 5,230 lambda. So negative 5,230 lambda is the natural log of 1/2. Natural log of 1/2 is the same as negative the natural log of 2. I'll let you figure that out if that's not clear. You need properties of logarithms to see that. So now it ends up being a particularly nice way to write the answer. If you divide both sides by negative 5,230, the negative signs divide out, leaving you with lambda equals natural log of 2 divided by the half-life, 5,230. And in fact, that kind of calculation is going to generalize. No matter what the half-life is, for the decay model written in the way we have it here, the lambda will be the natural log of 2 divided by whatever the half-life is. As far as applying it, though, you need to keep track of what the units are for time. In this case, years. So if I use this value of lambda, I need to make sure I use t as in years. If it were another problem where the half-life was in minutes, which is possible, then when you use the value of lambda you get from that, you'd want to make sure t is in minutes when you use the model. So you go ahead and replace the lambda with that number. You can get your calculator out and see what it equals. I forgot offhand. It's going to be a pretty small number, close to 0. That gets replaced. The lambda gets replaced with that quantity. And now you can use this to do problems. For example, in problem 12, they ask how old is a certain object that was alive in the past? When did it die? If, say, for example, 12% of the original carbon-14 is left. Carbon-14 basically stays constant in living things, but when they die, it decays off. And so you can use it to estimate how old something is. To do that kind of problem, if you've got 12% of what you started with, what you could do is you can replace q with 0.12 times q0. It really doesn't matter what you start with. Divide the q0s out again, and solve that equation for t. And that would tell you how old it is. Essentially, t equals 0 is representing the time the thing died. And then solving for t in this equation is telling you that, therefore, how much time has gone by, and therefore how old the object is. So that's my little push to get you started on the homework problems from section 1.1. There are also a couple of problems at the very end related to another model in section 1.1, something called a predator-prey model. It's got 2 dependent variables labeled R and F in the book for rabbits and foxes. Even though evidently foxes don't eat rabbits, we pretend they do. It's fun to pretend they do in that problem, and treat it as a predator-prey model, the predator being the foxes, the prey being the rabbits. Don't have time for this video, but maybe I'll make, in this video to do that, but maybe I'll make another short video here in a moment and talk about that problem. But we'll end this video here now.